This talk is about effects and concurrency in functional programming. And well, now that I think about it, I don't have too many effects in it, but I hope it's fine. Anyway, I'm Alex. I work at ING. I'm a library author because that's what I do when I get bored. And before Scala, these are the programming languages I tried. I worked on the job with them. PHP, Perl, Python, C#, JavaScript, Java. But I have others post-Scala. But anyway, Scala satisfied me in a way that the others didn't. And I'm not sure how much it's about the language, but about the culture behind the language of the community in it. And it's a culture of functional programming. And this is what I'm going to talk to you about today. I'm not sure how much I'm able to cover in 30 minutes, but anyway. This talk is basically about craftsmanship, about building better software, because I'm obsessed about it. Ever since I read about it, I'm obsessed with the idea of meta-linguistic abstraction, by the way, an idea I got from structuring and interpretation of computer programs. But anyway, a good question to ask is this still relevant? I mean, are you afraid about your job, by the way? So but yeah, what is the job of the software developer? Are we made obsolete? Is craftsmanship obsolete? And I don't think it is. It's like saying that math is obsolete. The job of the software developer is not to translate business requirements into a language that the CPU understands, even though that's part of the job. I think the primary job of the software developer is to understand, model, predict natural phenomena, and that's basically math. Software is math. And nothing makes that more clear than functional programming. This is an interview question, by the way. What is functional programming? And it's programming with mathematical functions. And I'm emphasizing on math because, as software developers, we tend to overload terms like functions when we mean subroutines, like addresses in code where we jump, we do a long jump, and then we execute instructions that are side effectful. That's basically a definition I saw in my 9th grade, I think, and once you get used to math language, it's basically, really precise. Like a math function is one where whatever x or y from the domain, if f of x is different from f of y means that x is different from y. And this basically tells you that given an input, you always get the same output. It's talking about determinism, right? You don't get like an association with two arrows from the domain from the same value. Anyway, the stated benefits from zealots, such as myself, of functional programming are basically local reasoning, which is about decoupling code from its surrounding context, reasoning about the code different from its surrounding context. Of course, you have some local reasoning using other techniques, which is why, for instance, Linus Torvalds is against C++ and likes C. I mean, I wouldn't say C is good at local reasoning, but who am I to judge? Anyway, equational reasoning. Equational reasoning is about, how in 6th grade we teach our children to solve first grade equations, right? By replacing them with simplified expressions, and the expression still works. It still has the same truth value. So it's about refactoring, meaning you can take an expression and you can refactor it without changing its meaning because we are operating with mathematical laws in functional programming. And we know what we are able to replace. And composition, although functional programming doesn't have a monopoly on composition, I mean, object-oriented programming composes just fine, but when composing functions, nothing composes easier, sorry. And category theory. So, but going beyond that, we are talking about easier refactoring. I already mentioned it, meaning that you can move pieces of code around. Rust is not a functional programming language. Sorry. Have you ever tried refactoring Rust? I mean, can't do it. Lawful observable state modeling, and here I'm talking about immutable data structures, finite state machines, evolved via pure functions that are deterministic, that are easy to test. Testing outputs, not side effects. Who here loves mocks? I don't. I mean, I'm just raising my hand to encourage you to be truthful about it. But whenever I see a mock in testing, whenever I feel obliged to add a mock in testing, I feel bad about myself. And did I forget to mention that I may be talking trash about your favorite techniques and tools? Sorry. Forcing resources to be parameters, clear dependencies, and safe life cycles. And this is a big one, and it's a subtle difference with regular programming. And by resources, I mean everything. And one interview question. What are side effects? What are pure functions? The first function is definitely a pure function. It's a math function. We are just adding one. The second function, I actually got a response in an interview, in a technical interview, that the second function is pure, because that randomized value has to do with the output of the function. He probably read a certain book from a certain uncle, but it's incorrect, right? It's non-deterministic. And the third function, buzz, what do you think about it? Is it pure or it's side effectful? Well, we can test it, right? Referential transparency is the test we make, and it's talking about the ability to replace the call, a function call, with its result. If we replace the function call with its result and it doesn't change the observable effect of the program, then the function is pure. In this case, it's not. Because, I mean, here we've got like two values, A and B, being assigned a new array. We mutate the first array, and then we print the second. We get some result, right? If we modify this function to reuse the first value, which should have been possible if that function were pure, then we don't get the same result. This is like a really useful test that sometimes we can even use in unit testing, although you have to be careful about it. Array is a resource that needs to be passed around as a parameter, by the way, and initialized in a way that doesn't give surprises, maybe, suspended in I/O. So I like to define terms. What is concurrency? What is parallelism? I got this slide from a book, something in Manning, but I added the source there. It's really good. Concurrency is about is a semantic property of tasks, right? Semantic meaning that you have the programming language gives you the possibility of marking tasks that can be independently executed, and they can start at the same time. So we are talking about independent tasks that can start at the same time. Parallelism is a property of the runtime. It's not a semantic property. It's a property of the runtime, meaning that some runtimes, like the JVM, have the ability to run concurrent tasks in parallel. So just to get this straight, we are talking about concurrency most of the time. And one thing that I want to get across is that concurrency problems are ordering problems. Or maybe we can think about them as interdependence problems. Whenever you have a concurrency issue in your code, it's about your code executing in an order that you did not expect. Maybe because you're running on a different CPU architecture. Maybe it's because you haven't foreseen the effects of, I don't know, the communication protocol. And this is not only about multi-threading issues. It's also about problems in the communication protocol, as I said. Like, I don't know, in our case, we can have reversals of transactions that are concurrent with the actual processing of the transaction. And of course, you have to protect those. Now, sequential execution. Sequential execution follows a really simple model, and it worked out fine. And this is about, blocking I/O. This is Java before version 8. This is how people did things. Right, so fetch profile does, I don't know, a query to some database, like in most apps. Fetch order does another query. We build crude apps, right? So we then launch delivery and commit, and these are all using blocking I/O, meaning that they block the underlying thread. But they follow a really good mental model, right? When we are doing programming, the mental model matters. I mean, how we explain, the CPU is not sequential, right? The CPU has a lot of optimizations, but from our point of view, these instructions are sequential. And this helps us. I mean, when we first learned programming, we learned it by, I don't know, doing a recipe for pancakes. In order, right? You take some eggs, you mix them, blah, blah. I don't know how to make pancakes. But the problem with blocking platform threads was that blocking threads is expensive in terms of CPU, in terms of memory, context switching, cache thrashing, and also I'm highlighting here a Wikipedia page talking about slow loris, which was a really effective attack against Java servers that used one thread per request. It was basically starting a request, sending a couple of bytes, and then freezing, which quickly depleted all available threads on that server, and it would crash it, right? It was really fun. And this was something built in Perl or something. It was genius. So the answer was to switch to asynchronous I/O, meaning that we use like an abstraction like future promises in JavaScript. C# pioneered it, by the way, this syntax async await. Java 8 came with completable future, but anyway, this was pioneered by C#, then entering TypeScript and ECMAScript. And the idea here is that you mark functions with async, and then whenever you do an asynchronous call and you want to wait for its result, to do a sort of semantic blocking, you use an await. Now, people complain about function coloring here, right? And it's a problem, but I actually like function coloring. Function coloring is not the problem if it's done correctly. There are other issues with this piece of code, which I'm going to talk about next, as you imagine. But by the way, I hope you're familiar with Scala syntax, right? I love Scala. I hope you do too. So this is the equivalent of Scala. It's using for comprehensions, like a syntax that translates. Here too, the compiler basically takes these expressions and turns them into a state machine that can suspend execution until the asynchronous result of the operation is done. And here too, basically the compiler takes this for expression and turns it into calls to flat map, right? Flat map. Have you received the gospel of flat map? And it's sequential. It looks sequential, right? It's using future. But future sucks. And it sucks because it can lead to accidental concurrency, right? Here, we basically call those functions, but we forget to await on the result. And maybe this is intentional. Maybe we want parallel execution. But maybe it's not intentional because it invalidates our mental model about how algorithms are described as a sequence of steps. So I got burned by this, by the way. I got burned by this. And you need trained eyes to spot mistakes in such code. And this can manifest in TypeScript as well, and JavaScript and C#. I mean, you forget the await keyword. And you've got unintended accidental concurrency, right? Maybe fetch profile and maybe fetch order are not meant to be executed in parallel. That commit surely doesn't look okay, right? Maybe it should have happened after we awaited, right? And here's another problem. We start with blocking I/O. We've got a commit that does blocking I/O, and we've got a call side that calls commit, right? But we hear about blocking threads being bad, so we refactor it. And now we've got, again, accidental concurrency because the compiler doesn't complain. The C# compiler, I think it started emitting some kind of warning in some instances, but it can't complain too much about it because this could be by design, right? I mean, the implicit behavior when calling this commit, because it returns the fuzzy, it's asynchronous execution, right? If you want to make it synchronous blocking, you have to use a keyword, or you have to make an effort to wait. This is the wrong mental model. This is why it sucks. So another problem. This one is on marketing materials for the new toolkits on structured concurrency from Kotlin and Java 20 something. We do concurrent execution on purpose. We start those two concurrent threads, but one of them throws the first one. What happens with the other one? We have got a leaked resource, right? Maybe fetch order is expensive, and throwing that error exposes us to resource leaks. We need to cancel it. This assuming that we have a usable interruption protocol, of course. Future doesn't have one. Another one, right? I can, just by looking at this function, you should see that it's a leaky function, because Future doesn't have a usable interruption protocol, and in case a timeout happens, the idea here being that after we await, after a certain duration, we get a timeout exception to do something useful with it, like you only have 3 seconds to do something, then bail out and do something else. But we don't have a usable interruption protocol here. Actually, when I look at APIs, at Java APIs, I actually prefer the blocking versions. The blocking I/O versions, because they are saner, because you can use Java's interruption protocol with thread interrupt. It's imperfect, it doesn't work in all cases. Java developers ignore it and hide interrupted exception and so on. But at least it's there, right? When Future completely hides that. And I'm talking about completable Future as well. C# has a usable interruption protocol, but it's weird, and I don't like it. Now, let's talk about Scala and the cats effect library. Initially, this presentation was in Romanian, by the way, so this is why I wondered how to translate that. And that's 𝗍𝐶, my cat. She's the mascot for this talk. Every successful presentation has to have a cat. We are going to switch to I/O. And we already got a preview of I/O in the first presentation. And I/O is a data type that resembles Future, except that it suspends side effects. It's basically a subroutine, a side effectful subroutine that hasn't been executed yet, and we operate on it by, applying the available combinators on it. This program is completely equivalent to the one using future. I mean, it looks the same. It's not equivalent. It looks the same. But it has a completely different behavior. We are calling those functions there, right? Fetch profile, fetch order, but that's not where they execute. That's not where the side effects execute. That's just a description of what will execute. And the fourth comprehension below basically described another unexecuted I/O that represents a computation that represents our intent. And if we refactor this program to not use those 𝗵𝐸𝐻 values, it has the same behavior. You cannot make this program to have accidental concurrent execution because it will always process these steps in sequence because that's how I/O works. Everything is explicit about it. In case we are refactoring a function, now this is where things get a little bit weird because it depends on what the compiler does, but the compiler has all the data it needs to emit an error. And the Scala compiler, God bless its heart, can emit errors in case we've got an unused I/O value. If you have an unused I/O value, it's probably a bug. So we can do that. And just as a side note here, Kotlin's coroutines are also doing the right thing. If you turn a function from a plain function to a suspending one, it will also emit an error. So equivalent. I like having the compiler protect me, especially when I'm stupid. So explicit parallelism. If you want parallelism, we need to be explicit about it. This is a sample where we are using a combinator called per map, but there are others, per traverse, per sequence. And we specify that those two tasks are independent and need to be executed concurrently. Explicit. Right? Now, maybe this doesn't work right for all algorithms. I mean, maybe you want to work in some environment where parallelism is more like implicit rather than explicit. But this is not how we program for the CPU. I mean, if you want parallelism, implicit parallelism, go program the GPU or something. And race conditions, also explicit. And this is where things get interesting. Here is something like we had in production. We process instant payments, and it's a soft real-time system, meaning that we've got 10 seconds at most to reply to the client. And we have an internal queue that receives transactions, and we had a timeout installed on it. If 10 seconds passed, then we give up. Now, a question. So, by the way, this here works with I/O because it's a value that whose execution hasn't started yet, and the implementation has a certain leeway in how it gets executed. It also has a usable interruption protocol. This means that we can install a timeout on it. This doesn't happen necessarily with other pieces of technology. This is why timeouts in Java libraries are a part of the framework. Like, you initialize the resource, and in its configuration, you tell it how you give it a timeout configuration. You can't install a timeout after the fact, right? But when you get an I/O value, you can raise it with a timeout that will throw a timeout exception, and it will cancel the original task if the timeout succeeds. Now, this piece of code here is actually problematic. Even with 𝐾ATS effect, by the way. Even with 𝐾ATS effect, we could have a problem. Fortunately, we don't. We could have the problem that timeout is still a concurrent operation, and when a timeout exception actually gets triggered, the transaction might have entered the queue. Fortunately, 𝐾ATS effect has being the lawful library that it is, lawful meaning that it's based on a small set of primitive operations that then get combined in useful ways, and it has a really useful interruption protocol, really well-defined meaning. In this case, when you get a timeout exception, you get the guarantee that the transaction hasn't entered the queue. This is real. So you can say HTTP 429, too many transactions, retry later, or maybe not. If the transaction would have entered the queue, then you would have to process it, and you can't say HTTP 429, right? This can work somewhat with Java's interruption protocol, but that's only because I know how to use it, right? Because it's low level, it's error prone. But it works. I mean, it works. It works. With Kotlin, I would have issues, by the way. I would have issues implementing this in Kotlin. In Java, it works because that blocking queue there implementation will emit an interrupted exception when it gets interrupted, and then you kind of have the guarantee that the transaction hasn't entered the queue. But you still have to be careful about it, which is why I'm using a Boolean there to know that the actual operation that emitted that exception, and then we are catching the interrupted exception, and we are then proceeding with operating as if everything is normal, and of course it's not. I mean, this is one of the problems with the interruption protocol in Java, because you can continue operation as if everything didn't happen, yeah. And many people just catch that interrupted exception and ignore it. And this is a problem, and I could probably refactor it, but it leaves something to be desired here. I hope that once those structured concurrency utilities enter, like Java 24 or something, we'll have a more usable solution to problems like this. With timeout there is something I made up. I could implement it. It's not really hard, but you have to be careful about thread interrupt, right? So I wanted to talk a lot about in this presentation, but 30 minutes. 𝐾AT's performance is awesome, by the way. It exceeds that of Project Loom. I noticed a little concern about boxing, by the way, when using like these types. Guys, come on. You shouldn't be using Java if you're worried about boxing. But anyway, in my experience, the performance issues tend to be dominated by I/O, even in highly concurrent, highly scalable systems. The garbage collector is an issue. Actually, the biggest issue is indirection, but the biggest issue is interaction. Because the garbage collector actually does a splendid job. And by the way, Project Valhalla, there's a misunderstanding about Project Valhalla being about stack allocation. It's actually not about stack allocation, it's about allocating contiguous memory regions in order to avoid indirection, because otherwise the garbage collector is pretty good. Anyway, the interruption protocol, you need one. And you need a usable one. By the way, I/O in 𝐾AT's effect resembles Mono from Project Reactor in Java, except that the interruption protocol is less stellar, and it doesn't have a tail recursive flat map. Resource is a superpower. I wish I would have talked about it. It's really great. I mean, I don't know how you can use Spring, sorry. Ref and deferred, queue and semaphore, 𝐾AT's effect provides a really cool standard library of stuff. And parametricity is basically the opposite of encapsulation.